Thanks to the organizers for having me, and thanks to all of you for being here this morning. And thanks to my co-authors, Rob Wilson, Jessica Tierney, Allegra Legrand. Is that loud, or is it just me? And also, this is a product of both work by the Pages 2K Oceans 2K High-Res Group, as well as the N-Trend Consortium that Rob Wilson and I and about 20 other people have been working with. So I'm going to talk today about volcanic forcing of climate of the Common Era, and as I'll show you in a moment, this really is one of the most important forcings, certainly at least until the rise of anthropogenic CO2 in controlling climate over the last 2 millennia. So what you're looking at here are experiments done with the NASA GISS model using both single and mixed or full forcings, and along the top is the 2 volcanic forcing series that were used for the latest CMIP and PMIP runs, the range of solar variability, and I'll call your attention to the fact that these scales are very different. And so you look at the large eruption of Somales, the middle 15th century eruptions, these are quite significant radiative perturbations. Now you can run the GISS model, or you can run any model with some of these forcings, or leave some out, and so the bottom panel shows you 2 simulations. In the red is forced only by solar variability as well as well-mixed greenhouse gases. And then the black line shows a simulation with volcanic forcing added in. And you can see the rather large global mean temperature response that results. And not simply associated with the individual events, but when many of these events occur in sequence, you can actually generate substantial decadal variability. So we'd like to understand better the role of volcanic forcing over the Common Era. Despite the fact that this is a very important forcing, there are some large uncertainties in how it affects the climate system on these timescales. For one, there's multiple lines of evidence that many, if not most models, overestimate the cooling in response to these volcanic eruptions. There's several reasons why this might be. And then a very interesting feature that's gotten a lot of attention over the last several years, but actually goes back at least into the 1980s, is this idea that large tropical volcanic eruptions can actually initiate or cause an El Nino event. There was much debate about this in the 80s and the 90s, and then in 2003, Adams et al., using the reconstruction from Mann et al. And extracting the El Nino region, noticed that for a range of eruptions, it appeared that an El Nino event followed 1 or 2 years after an eruption. Some climate models can reproduce this behavior, others can't. There's been continued debate about whether this is a robust feature. And one of the things I'll talk about today is how we see this in our new reconstructions of tropical Pacific sea surface temperatures. So I'm going to show you 2 different data sets. This is our just published spatial reconstruction of from the Northern Hemisphere tree ring network development. We published a Northern Hemisphere summer reconstruction last year, and we have now a spatial reconstruction using this network of tree ring chronologies. This is quite a temperature-sensitive network, 54 chronologies, all of them responding quite strongly to summer temperatures, in some cases resolving 60, 70, 80% of the instrumental variance. So this is a very strong temperature-responding network, very sensitive. And what's nice about doing these spatial reconstructions is we can look at how climate responds not simply in the temporal domain, but also across space. So this is just one example of the cooling that followed Krakatoa in 1883. Here you can see the full field observations from Cowton and Way. And then here's our, laser's not going to survive. Here's our full field reconstruction using the tree ring network. So we can do quite well in reproducing the spatial patterns that result from really a range of forcings, but in particular here, volcanic forcing. So you can look over all the large events, large eruptions, large tropical eruptions identified by Michael Sigel and his colleagues in their recent reanalysis of the volcanic ice core record, the sulfate ice core record. You can composite over all these events, and what you see is a very clear post-volcanic, post-tropical volcanic cooling pattern. So in our reconstruction, it cools nearly everywhere. And so we see a very clear, very robust evidence in this reconstruction of the cooling that follows large volcanic events. But of course, compositing tells you maybe something about the general response of the climate system, but we can also then dig down, use the fact that we have this annual resolution, look at these maps, and actually see what different eruptions look like. And so this is a very interesting eruption. This is the 1809 unidentified event so far, the cooling that follows it. But what you see is that if you move away from some sort of global or hemisphere mean average, that there's actually some structure here. So cooling over Fennoscandia and northern Europe, cooling over Alaska and the western North America, but actually, and we know this quite well, an actual warming signal that appears over the northeastern part of North America, perhaps suggesting some sort of dynamical response as much as a radiative response. So we can actually zoom in and see the spatial patterns of this and what it might suggest, not simply about how global mean temperatures respond, but how atmospheric circulation responds. We can average, we can create a large-scale hemispheric average, we can smooth it, and we can see the importance of these various modes, or sorry, these various features of radiative forcing. So prior to the onset of large-scale anthropogenic CO2 emissions, there's a relationship between solar variability and really also you see major cooling events associated with these clusters of volcanic events, sort of a two-stage step into the Little Ice Age, first following the late 13th century cluster of eruptions, and then a real cooling that happens around 1450, coincident with the spore minimum, but also with these large middle 1400s eruptions. And then, of course, the signal in the last several decades emerging as an anthropogenic global warming signal. Now, what about this idea that perhaps models overestimate the cooling associated with volcanic eruptions? This is from Wilson et al., Rob Wilson et al.'s paper. You're looking at our hemisphere reconstruction there in red, an earlier reconstruction in the blue, and Leah Schneider's Turing density reconstruction in the green for two sets of volcanic events. And what you see in the gray and the black are a selection of CMIP-5, PMIP-3 last millennium runs, past 2,000-year runs. And what you see is that overall the models do have more cooling than any of these three eruptions, that there is a long tail, at least in the reconstructions from the tree rings, that is seen in the SIGL events, but not in this Gao-Crowley list. So there's still some uncertainty here, but this does support this emerging line of evidence that the models cool a little bit too much in response to these eruptions, at least compared to the paleo data. So the second set of data I want to show you actually come from Pages 2K work done by the Oceans 2K High Resolution Group, led by Jess Tierney. And in this, we used a network of coral data, you can see here in the white circles, to reconstruct sea surface temperature, annual sea surface temperatures in 4 boxes, a West Atlantic, Eastern Pacific, Western Pacific, and Indian Ocean box. So there is some spatial characteristic to these reconstructions. Each box is independent. It doesn't share any coral data with any other box. And what we can use this to do is start to look at not simply the magnitude of the climate response to volcanic forcing in the tropical Indo-Pacific, but also how this varies in space. So this is a bit of a complicated checkerboard, but let me take you through it. Each column is associated with a different eruption. So you can see Parker here, the unidentified eruption in 1809, Krakatoa here. So each row represents a large tropical volcanic eruption. The forcing in watts per meter squared from the different data sets is along the top row. This is converting sulfate loading through AOD to a watt per meter squared estimate of the forcing. And then we have our Eastern Pacific reconstruction, Western and Indian Ocean along the bottom. The blue lines are the ensemble reconstructions, and the heavy black line represents the best, most skillful ensemble. So Oceans 2K actually created an ensemble reconstruction so we can do some uncertainty analysis. And then the red lines show the actual observations. So what we can do is we can do this superposed epoch analysis. We can go in and composite each different region of the tropical Indo-Pacific for each one of these eruptions and see what the overall response to volcanic forcing is. We can also compare this to a set of CMIP, PMIP-3 past 1,000 eruptions. And the general picture is this, that the Indian Ocean cools, the Western Pacific cools. This cooling lasts for about a year or two, significant cooling. And then the Eastern Pacific is more ambiguous. So there is a slight warming, but only some of the ensemble members show this to be significant about 2 years after the event. Now, the color lines are different models, and what you see is that all the models want to cool in the Indian, the Western Pacific, as well as the Eastern Pacific, and some of them want to cool quite a bit more than the reconstructions. But in general, there's an overestimate by the models compared to the coral reconstruction. Now, interestingly enough, which model cools more doesn't seem to be connected to anything like the climate sensitivity of the models. And if you look at, say, two models, the blue is CCSM4, which cools a lot. Purple is BCC, which cools very little in response to these eruptions. They have nearly identical climate sensitivities, and they use the same forcing series. So what explains this difference? Near as we can tell, what's most important is the actual implementation of the forcings in the model. It depends on how you're actually imposing these eruptions, how the sulfate loading is calculated, and how this then appears in terms of the top of the atmosphere forcing. So it's not about climate sensitivity of the models, it's not about even the forcing series so much as the difference between models is driven by how they implement the forcing. Now, the last thing I want to talk about is what do these new coral records say about this idea that El Niño events follow tropical eruptions? What we see is that there's consistent cooling in the Indian and the West Pacific, and an inconsistent and relatively small magnitude of composite warming in the Eastern tropical Pacific. And so this suggests that, one, there is a change in the gradient, that you actually cool the warm pool and you might slightly warm the cold tongue. But this isn't really ENSO-like. What's really happening is a cooling of the Indian and the Western Pacific. So in some ways, what this spatial reconstruction of corals, from corals suggests is that the sort of paradigm of El Niño or not El Niño may be too simplistic, that what we're looking at here is really a change in the gradient that could have similar teleconnections, that could have similar global consequences, but this isn't El Niño per se. And so with that, I'll lead up my conclusions. I'll say one thing for doing terrestrial reconstructions is we need many more density proxies. These are much better triggering proxies for reconstructing temperature. And I think that one of the takeaways from this is that talking necessarily about ENSO may actually not be as useful as talking about changes in the gradients across the Pacific in response to these eruptions. Thanks very much.
Kevin, I'm just curious if you looked at whether or not the preconditioning, the conditions in the tropical Pacific prior to the eruption mattered as far as the response that you got.
Yeah, we're looking at that. I don't have any of those results to show you. There's been two complications in doing that, a relatively small number of events. And so I don't know how well we're sampling the three potential preconditions. And then the most uncertain part of the Oceans 2K reconstruction was actually the Eastern Tropical Pacific, and so that also complicates this relatively small number of eruptions. So we're looking at trying to resolve this a little bit, and I think we can do it, but I'm not really confident saying yet. But I think preconditioning is something that's been shown to probably be important, at least in the model sense, and so we may be able to shed some light on this, but I can't do so yet.
Okay, so thanks for having me to speak. I'm really excited to be here today. And I wanted to present some results from an isotope-enabled regional ocean model that I've been working with. And I would have loved to actually be able to constrain El Niño properties during the last millennium, but my abstract may have been more ambitious than I could actually achieve. So I'm going to show you some results where I'm trying to move the community towards being able to do these kinds of things, and hopefully motivate everybody to think about new ways to forward model coral proxy records. And I want to just acknowledge my co-authors, Kim Cobb, Brian Powell, Mark Merrifield, and Jesse Nussbaumer. Okay, so as a motivation for this talk, there's been a lot of discussion about constraining ENSO variance throughout the Holocene. And this is just an example from Kim Cobb's paper a few years ago, where she finds an increase in variance during the late 20th century relative to the majority of the Holocene. And so this suggests that perhaps we're seeing some kind of anthropogenic impact on ENSO variability. So it would be great to know well, first of all, exactly how significant this variance increase is, but more importantly, from a climate modeling perspective, what are the physical mechanisms for this increase in variance? So are we seeing an increase in temperature variability? Are we seeing an increase in hydrological impacts? What is the spatial structure of this variance increase? And in order to, if we knew the answers to all these questions, then we'd be able to have more confidence in climate model projections of future ENSO variability, because we could say something about the physics that we are or are not capturing. And this is a complicated question because coral delta 18O, it really records a combination of influences. So this is kind of what I was alluding to just now. So we need to be able to disentangle temperature influences and influences from the delta 18O of seawater. So this is the equation for coral delta 18O showing those two influences. And what we know is that there's a strong influence on temperature. So basically, the inorganic aragonite fractionation leads to a change in the delta 18O of corals. And this is relatively well understood. I know some people in this room probably have slightly different slopes to this calibration curve. There's somewhat of a range to this, but in general, we think we know what's going on in terms of the temperature impact on corals. That's not nearly as well constrained for the delta 18O of seawater. So this is a function of a lot of different things. So just schematically, these are all the processes which affect the delta 18O of seawater. So you have influences from precipitation, from evaporation, from ocean dynamics, and we don't have a good handle on exactly how all of these processes link together to affect delta 18O of seawater. We do know that a lot of these processes are the same as the ones which affect salinity, and for that reason people often treat salinity and seawater delta 18 as proportional to each other. But I'm going to try to argue that this is not always what we should be doing, and in fact, maybe we can do better. So this is why I developed the isotope-enabled ROMs, or ISO-ROMs. So ROMs is the Regional Ocean Modeling System. And this is a good tool for this purpose because you can force it with observations. It's not a coupled climate model, so you don't have to deal with all of the biases in the mean climate that you get when you have a fully coupled simulation. And so the simulation was, or this tool was initially published in 2015, and I was able to simulate 1979 to 2009 at that time. But what I've been doing for the past few months is actually extending this further back. So we can now simulate the entire 1948 to 2009 period. So these are the configurations that I used for this particular simulation. So you have boundary conditions from an ocean state estimate, precipitative fluxes from the isotope-enabled CAMs, this is the atmosphere component of CESM, and physical forcings from the core 2 normal year forcing. So this allows us to create an actual approximation of a hindcast of seawater delta 18O over the late 20th century. So this is my attempt at creating as close to a fully three-dimensional time-varying observational product of seawater delta 18, given the observations that we already have. And we are now able to accurately simulate seawater delta 18O variations across the entire Pacific. So I wanted to show you 3 examples. This is actually one of the most poorly performing islands, so Palmyra Atoll. So we see that we do get these excursions towards negative isotopic anomalies during El Nino events. We seem to not quite capture the trend in seawater delta 18, which is kind of interesting, and I'm still working on figuring that out. So if anybody has ideas, I would love to hear them. But if you move further to the west, so in places like Butari Tari in the Gilbert Islands, we don't see that kind of a long-term trend, and we also are capturing not only the interannual variability, but also the decadal variability. So I should mention that these seawater delta 18 records, which are the black lines in these curves, are generated from paired coral delta 18 and strontium calcium. So these are completely independent sources of information. So we have 2 geochemical records being combined for the black curves, and then a model which doesn't actually incorporate any of that data is nonetheless able to represent the kinds of variability that we see in the real records. So this is pretty exciting. So this is a great tool for understanding the dynamics of these variations. And then just as the final example, here's a set of records from Quinn et al. In 2006. So we're able to capture the variability on these frequencies throughout a variety of different oceanic regimes as well. And I don't have any paired records for the Eastern Pacific at the moment, but hopefully that would also work. All right, so now we can ask the question, so we know that salinity and seawater delta 18 are affected by the same processes. So how are they related in this model? So we directly simulate them both. And what we see when we actually plot them versus one another is that the ROMS is capturing the basin or the regional average slope from the GISS data set. So that's about 0.27 per mil per PSU. And that's pretty much what we get in a lot of places. But there is large scatter nonetheless. So here the GISS slope is the dashed black line, and the red regression line is the line that you get from a local fit to the closest grid point to these 3 islands in ROMS. And you actually can't tell that the black line is dashed very well here because they lie straight on top of each other. So this is a nice illustration of the power of a tool like this, where you can actually try, we know that it's working approximately the way we think it should, but we can start to look at some of these details that make these relationships more complex. And I wanted to show you a couple of illustrations of the variability of these salinity and seawater delta 18 slopes. So here's a map of that relationship over the entire Pacific, right? So these are regressions just from 3 grid points. If you do that for the rest of the basin, then this is what you end up with. And you can see that there's a lot of spatial structure to this. And generally speaking, I get shallower slopes in the eastern Pacific and higher slopes in the western Pacific. And I had just finished making this plot when I saw Jess Conroy's new paper showing the actual observational slopes in 3 different locations spanning the East Pacific to the west. And she sees the same tendencies for shallower slopes in the east and steeper in the west. So it seems like there's a real physical process going on that ROMS is capturing. And I suspect that the reason why we see steeper slopes in the western Pacific has to do with the more complex nature of precipitation isotopic variability over the warm pool, which could lead to stronger variations in seawater delta 18O for a given variation in salinity. But that's something that I'm still trying to diagnose in the modeling framework. And then I just wanted to show that these relationships also vary in time. So the color bars here are a little bit different, but you can see that if you look at an earlier part of the ROM simulation versus a later part, then these slopes vary often really significantly. So for example, near Fiji, in the southwestern tropical Pacific, there's that big red blob in the earlier part of the record, which is that slope is much shallower in 1987 to 2009 period. So there's strong temporal variability as well. And actually, this might be considered a lower bound on the variation that you would expect if you were to do this in observations, because this is perfect information from the model over 2 chunks of time, which are both 20 years. So if you're just doing a site-specific sampling campaign, typically we're not able to do these for multiple decades, at least not yet. So if you only have a year or 2 worth of observations, then you might expect even more substantial scatter. So this is my attempt at improving the forward model so far, and just to motivate how complex this problem is. So this is not what I'm recommending we all do necessarily, but these are the terms in the seawater delta 18O budget. So you can look at these individual terms within the modeling framework, and we would want ideally to know something about the surface fluxes of both precipitation and evaporation in both H2 18O and H2 16O, the spatial structure of the water mass isotopic composition, and the role of diffusion and mixing. So if we want to improve these forward models, we need to take all these physical processes into account, and they're not always going to covary with salinity. So I'm running out of time right now, but I wanted to also illustrate an alternate way that these types of data might be used. So instead of just trying to translate directly between salinity and seawater delta 18, having a spatially complete data set would also allow us to exploit the covariances between sites in a physically consistent way and actually quantify the isotopic signatures of dynamical features. So this is just a picture of the coral and the seawater delta 18 during Eastern Pacific El Nino events. So this allows us to quantify the contribution of seawater delta 18 versus temperature to the coral isotopic signatures that we see. And so the point here is that if you have different types of El Nino events, you have different contributions of kind of the hydrological, like the seawater delta 18 versus temperature. And so this is something that I'm working towards actually being able to use to generate things like metrics of extreme El Nino events. Or one could imagine using this in a statistical sense, so applying techniques from climate field reconstruction, now that we know more about the covariance structure over the 20th century at least of the seawater isotopic fields. So that's kind of some future directions, and I think I should probably skip my plug for my observational campaign as well, but these are my conclusions. So there is this new tool now called the isotope-enabled ROMs. The model fields will be made available to the community after I finish looking at them. So contact me if you're interested. I'd love to collaborate with anybody who could make use of this. And just the relationship between salinity and seawater delta 18 is complicated. They are not the same variable, they are not functions of one another, they co-vary. And so we can use that knowledge as well as knowledge of things that affect the isotopic composition, but not necessarily salinity, to improve forward models of both seawater and coral delta 18. And we would like to ideally understand the dynamics of this behavior during different ensodynamical regimes and eventually exploit knowledge of different sites in order to understand how ensodynamics have varied over the Holocene in the 20th century. So, thanks very much.
Great job. I've heard about this work for a long time from Kim, and so I'm really happy to see it come to fruition. So just to be clear, none of the previous forward models that used salinity claimed that that was all there was to the story, right? We always knew it was more complicated than that, but we started from a state where people equaled delta 18 with temperature, so got to start someplace. One remark is that there's actually a really nice piece of work by Tom Russon with the HATCM3 isotope-enabled model that looked at this somewhat. What do you see? I mean, obviously ROMS is much more high resolution in how you ran it. What differences do you see between your work and his?
That's a good question. Oh, my microphone still works, right? I haven't directly compared my work with Tom's yet. This is still fairly preliminary, so I'd love to go back and do that. I imagine that we will see some fairly substantial differences, though, because when you're running with HATCM3 or another coupled model, then you're going to have differences in the mean climate and the ways in which different types of El Niños are simulated. So I don't know. I plan on looking at that and also looking at the new isotope-enabled CESM last millennium run, so there's going to be a lot of data to play with. But the goal here was just to do something that kind of more closely approximates observations as a different type of diagnostic tool. And I didn't mean to slam linear forward models either. I just would like to kind of get us beyond the point where we're thinking about this in the temperature and salinity framework. So.
Good morning, everybody. So the southern annular mode for short SAM is the most important climate mode in the southern hemisphere, extratropics. It influences climate widely over the southern hemisphere, like South America, South Africa, and Australasia. And I'll talk about the stability of the SAM teleconnections and some implications for SAM reconstructions over the past millennium. I'll start with showing you two already existing SAM reconstructions. One is from Nerli Abram, that's the black one, and then the red one is from Ricardo Villalba. And we can clearly see there's some major differences between those two reconstructions. I want to ask the question, why is that? Well, one reason is that they use a different set of proxies shown in the maps on the right-hand side. And they also did the reconstruction for different seasons. One is for DJF, that's Ricardo's, and Nerli's is for the annual SAM index, so that's also a difference. But maybe the teleconnections between the SAM and the regions hasn't been stable, which also might lead to some differences we see here. And the stability of teleconnections is important because such reconstructions rely on this stability. And that brings me to two research questions I'd like to ask. One is, how stable are the SAM teleconnections in the southern hemisphere? And the second one, what are the implications on SAM reconstructions if we use different stability criteria to do our proxy selections? And the second one is the question I'd like to focus on in this presentation. Talking about stability criteria, this is like an overview of the different methods we used. One is the Gershenov test based on running correlations, and it says you something about how if the running correlations are significantly more or less variable than could be expected by chance. The sign test just simply checks if the running correlations crosses the zero line or not. The Gallon test is a little bit more involved, but it's also based on running correlations. If you look at the relationship between SAM and climate, be it temperature or precipitation, it gives you kind of a confidence interval where you would expect the running correlations to stay in if the relationship was only influenced by local climate noise. And the fourth thing we're looking at is we do a model comparison. We have a model with time-varying coefficients versus a model with constant coefficients, and the AIC, the archaic information criterion, is used to do the model comparison. This is a brief example showing you two running correlation time series. On the upper one, a stable example. The lower one shows you a non-stable one. The red line in the graph, they relate to the AIC and show you the evolution of the coefficient. We call it lambda for the model, where this coefficient was allowed to vary over time. And in the top one, we can see it doesn't vary over time, so the model where we allow the coefficient to vary over time isn't better than just the constant coefficient model, where in contrast, in the lower graph, we can see that the red line is moving, so the time-varying coefficient model is performing better. Let me say, before coming to the results, how we use those stability criteria to select our proxies. Well, we did proxy screening and generated 4 different sets of proxies. One is just based on the correlations. One, we added those stability criteria. A third one is just the sign test as a separate kind of restrictive test. And the fourth proxy screening was just taking the original Villalba or Abram proxies for DJF and annual SAM reconstruction, respectively. The method we use is classical composite plus scale. This is an overview of the map where we have our proxies, 364 in total. And on the left-hand side is in red, just if you use the correlation-based screening. On the right-hand side, if you just impose the stability criteria additionally, the numbers are provided on the right-hand side. The results I want to present you are structured as follows. I will present you a few reconstructions for DJF, comparing to Villalba's, then a few results to Nerli's, to the annual SAM index, comparing to Nerli's reconstructions, and then also do a comparison where we do reconstructions using a short and a longer calibration period, with the advantage of the short one having better data and the advantage of the long calibration period having kind of a more reasonable time interval for our stability tests. Let me quickly guide you through that graph. We see on the x-axis the years, on the left-hand side, on the y-axis, the SAM anomalies with respect to 1905 to 2005. On the right-hand side, it's just the number of proxies. The gray shading shows the 90% confidence interval for the black reconstruction, and the yellow shading is the calibration period. If you look at the multi-decadal variability, we can see there's a really good match between all those reconstructions. And if you focus on the black versus the red one, where it's just a correlation-based screening, and the black one additionally with the stability criteria, you can also see a really good match between those. So kind of saying that the well-correlating proxies are also kind of the stable proxies, and that's kind of good news. And also on the multi-decadal timescale, if you compare it to Ricardo Villalba's reconstruction in green, we see a good match, although he used very few but high-quality proxies. For the annual SAM reconstruction, the picture doesn't look as clear as for DJF. We can see that they don't really agree as well. We have times where the red and the black line don't really agree well. So if we use the stability criteria, there seems to be some differences in the reconstructions. And also that the match to Nerli's reconstruction is not that good. But I have to say, we have a lot of tree ring proxies from the mid-latitude tree rings, and they're mainly DJF sensitive, so that might also be a reason for some differences we see. As promised, Here are the reconstructions where we use the shorter and the longer calibration period. The longer calibration period is the solid line, where the dashed line is the reconstructions for the short calibration interval. And again, for DJF, we see a very good picture that they match really well, besides maybe the very early data sparse region. But still, the picture looks really good. And that can be seen as a hint to more or less stable relationship between proxies and SAM. Moving again to the annual SAM index reconstructions and doing the same thing, we can see that the picture doesn't look that great again. We can see major differences. For instance, if looking at the red curve, if you use a short calibration interval versus the longer one, we can see really major differences. And if the teleconnections were stable, then the choice of the calibration period should not result in very big differences in the respective reconstructions. This is a plot I added to kind of emphasize what I said before. It's a 30 to 100 year bandpass filter, and it emphasizes the multi-decadal variability for the DJF reconstructions, and we can really see they kind of match perfectly. They're really highly correlated, no matter if we use just correlation-based screening or just impose the additional stability criterion. It's a really good match. So let me conclude by comparing the SAM reconstructions for DJF and the annual SAM index in one single plot. If comparing these two just together, we can see that for DJF we have kind of higher variability. And if you remember the first picture, Ricardo Villalba's reconstruction for DJF was just back to 1400, and we have now an extended SAM reconstruction back to 1000 AD for DJF. Both reconstructions have in common that they have the lowest SAM values around, let's say, 1480, around 1500, and then after that show a positive trend. The skill over the whole time period is better for DJF, as seen in the lowest part where the reduction of error statistics is shown. Okay, I'll finish with, as I said before, some conclusions. We have the extended SAM reconstructions for DJF. If you look at the summer SAM reconstructions, they're really robust. They do not really depend on the choice of the calibration period and also the criteria for teleconnections stability we imposed on it. Whereas for the annual SAM reconstructions, things look a lot more uncertain. Thanks a lot.
I wonder if you've addressed the question of how the reconstruction agreement might be influenced by the changing number of available observations per unit time. So I'm wondering if you've done the simple experiment of using only the data that are available for the full millennium and seeing how those compare.
No, I haven't a comparison for that case. No, I can't tell you how the results would look like if you just use the very few proxies for the whole record. I can't tell you.
Have you tried comparing the stability of the teleconnections within the proxies with the stability of those relationships within the climate model simulations? For example, the PMIP3 last millennium ensemble?
No, we didn't look at climate, at models for that case. That would kind of be too much things coming together, but it would be very interesting to see how models also perform in comparison to the stability, yeah.
Thank you. Today I'm going to talk about some of my PhD research that focuses on data reduction techniques to identify climate signals within Southeast Australian paleoclimate records. First, I'd like to thank my co-authors, without whom this research would not be possible. So we have a lot to cover. Today I'm going to talk to you about why we're interested in looking at the past 2,000 years in the Australasian region. I'll talk about why we need to use low resolution or non-annually resolved data to look at this time frame, and talk to you about the current state of the data network within this region. I'll briefly discuss the Bayesian age modeling that I've been conducting, and then I'll go into detail about a study that we've conducted that looks at climate signals at both the site level and the regional level within Australia. And then I'll compare the outcomes with existing paleoclimate reconstructions, and then briefly discuss the outcomes of this study. So we're interested in looking at the past 2,000 years in Australasia for some of the same reasons why we study this time period in other parts of the world. For the past 2,000 years, we have the highest quality paleoclimate data. We have a good understanding of the boundary conditions during this time. And within Australia, we do see regional climate variability that is similar to the Little Ice Age and the medieval climate anomaly. We have both annually resolved and non-annually resolved paleoclimate data within this time. Previous studies have identified the annually resolved paleoclimate data in the form of coral records, tree rings, and ice cores. However, the vast majority of these records only extend for approximately the past 300 years. For this reason, we're interested in complementing the high-resolution records with the non-annually resolved records to be able to look further back in time. Within Australia, we do see a medieval climate anomaly and Little Ice Age type anomalies. Previous studies have reconstructed the hemispheric circulation patterns within the medieval climate anomaly and have identified very rapid shifts in the location of the subtropical ridge, which controls the influence of the tropical climate variability versus the mid-latitude climate. The Little Ice Age has been investigated at more of a site-by-site approach, but at the same time, we do see that there is increased effective moisture during this time and decreased general variability. Within both the medieval climate anomaly and the Little Ice Age periods, the main feature that we see is very pronounced multi-decadal variability. For this, when we're wanting to examine multi-decadal variability, we want to use long continuous records that extend for multiple centuries back through time. Recent literature search identified all of the non-annually resolved paleoclimate records extending through the past 2,000 years. 665 non-annually resolved records were identified, and these fall into 4 categories: lake and wetland records, marine records, speleothem records, and geomorphic records. Of these 665 records, only 22 of these records were categorized as high-quality data sets. The high-quality data sets were identified through the application of 5 selection criteria: a robust climate proxy relationship, record length extending at least 500 years, an age model based on at least 2 or 3 dates, average sample resolution between 2 and 50 years, and record location within the Australasian region. When we examine the 22 high-quality paleoclimate records, we see that they fall within 2 distinct geographic regions. One region is within the maritime continent, and the other region is within Southeast Australia. For our study, we focus on the records that exist within Southeast Australia. You do see that there is one record located within New Zealand, but this dust accumulation record is interpreted to represent Australian aridity. Of the 10 records that fall within Southeast Australia, 9 of these records represent hydroclimate. For this reason, we wanted to investigate the hydroclimate variability within the past 2,000 years. The records that fall within this region come from a diversity of archives and have a diversity of proxies measured within them. For this reason, we have a unique opportunity to be able to assess the similarity of climate signals between archives. We know from previous studies that each archive and each proxy has differences in the strength of the climate signal preserved and the method in which the climate signal is preserved within the proxy. The first step in examining the variability within this region is to create new age models for each of the 9 hydroclimate-sensitive records that we've identified. The construction of new age chronologies allow us the opportunity to incorporate site-specific knowledge into a Bayesian framework. It allows us to have a consistent approach in all of the age models, just to be able to remove that source of uncertainty. And also, the Monte Carlo approach to age modeling within the Bacon software allows us to quantify the age uncertainties and then furthermore, allows us to create time-uncertain time series like what you see on the right-hand side of the screen. Once we have new age models, then we can shift our attention to the multi-proxy records within some of the individual climate records. 5 of the 9 sites have at least one proxy five of the sites have more than one proxy interpreted to be hydroclimatically sensitive. And what we're interested in doing is to pull the pure climate signal out of these multi-proxy sites. In order to do this, we performed data reduction techniques, either principal component analysis or detrended correspondence analysis, depending on the type of data from the individual sites. We performed these data reduction techniques 10,000 times, so not only does it incorporate the age uncertainty, but it also incorporates the uncertainty of the record through time. So we've retained the first 2 modes of variability for each of these 5 multi-proxy sites, as you see on the screen. And just from visual examination, we see that there are some consistencies between these time series. These consistencies suggest that there is indeed a climatic feature driving some of this variability. Now that we've identified the climate signals at the site level, the next move is to shift to the regional identification of climate variability. In order to do this, we performed a regional principal component analysis, which incorporated the 10 time series from the multi-proxy sites, in addition to 4 time series from single proxy sites. These 14 time series were loaded into a principal component analysis in order to identify regional modes of variability across the 9 paleoclimate sites. The outcome of our regional principal component analysis is seen on the screen. We retained the first 3 modes of variability that were hypothesized to be significant through the broken stick plot. The first axis that you see in red shows a steady decrease towards the present. The second mode of variability shows 2 peaks, one at approximately 1100 CE and another at approximately 1500 CE. And then the third mode that you see in green, the main feature of this mode is a very sharp peak at approximately 1100 CE. Our next step was to compare these outcomes to pre-existing paleoclimate reconstructions that represent possible climate drivers within this region. When we compared our principal component analysis modes to the existing paleoclimate reconstructions, mode number 1 showed the greatest match with the El Nino Southern Oscillation variability through time. The second mode of variability showed the greatest match with the Southern Annular Mode through time. And then the third mode, we see that the main feature of mode number 3 is a peak that occurs approximately during the medieval climate anomaly. Previous studies have identified flooding in central Australia around this time caused by an increased transport of moisture from the Indian Ocean across the Australian continent through very strong northwest cloud bands. Therefore, we hypothesize that mode number 3 may reflect the influence of the Indian Ocean on the Australian continent. Overall, Australasia has hundreds of climate records covering the past 2,000 years. However, our studies have shown that only very few of these are actually suitable for assessing multi-decadal climate variability during the Common Era. Iterative age modeling provides very important uncertainty estimates within paleoclimate records. Dominant signals can be seen in multi-proxy site-specific records. And when the modes of variability within these individual sites are compared, we can see regional intrasite patterns. These regional patterns that we identify show agreement, we hypothesize that they represent hydroclimate variability over the past 2,000 years and show agreement with the recent OS2K temperature reconstruction, El Nino Southern Oscillation reconstruction, and westerly wind strength. Thank you for your attention. I'm happy to take questions.
before you did your PCA, you looked at the sites that had multiple proxies for each site. So I'm wondering, it's possible that different proxies from the same site are just picking up different aspects of the hydroclimate system. So I'm wondering if you tried the PCA without doing that, if you just put everything, treated it as an independent record, what would happen? Or did you try that?
I haven't done that yet, but that's a good idea. I'll do that.
I will talk about South American monsoon over the last 2,000 years, using some delta TNU records in stalagmites. I'm from Universidade de São Paulo, Brazil, and there are my main co-authors. In 2012, we published this paper, and when we did a review of the South American monsoon over the last 2,000 years. And at that point, we just have 5 records available. Basically, all records was in Andes, Peruvian Andes, with the point 1, 2, and 5. And other record available was the point 4. The point 6 was in preparation at that time, was not included in that paper. What our records show in that moment was basically similar conditions. For example, during medieval climate anomaly, our records show dry conditions. During Little Ice Age period, it was wet conditions. And during current warm period, it was drier conditions again. And there, this comparison with all this record with North Hemisphere temperature. All this variability has a good fit with North Hemisphere temperature because when you have a more colder condition in North Hemisphere, ITCZ going to south, you have more moisture coming inside of South American monsoon. It opposed to happen when you have a warmer condition in North Hemisphere. Okay, this was in the interpretation with these records. Today we show 3 new records, which are in yellow in this picture, in the point 3, 4, and 5. And also in this map has other records we were already published or in our preparation. We are also able to compare here. And we see with some new records, the history change a bit. I will start to talk about the point 3. Our study site in point 3, we have a monitoring. We did this monitoring for around 3 years. When we collect the rainfall water, we measure the delta TNU of this water, amount of precipitation, and other environmental parameters inside of caves. And we calibrate for these study sites the relationship between delta TNU and amount of precipitation. In this picture, we show the youngest part of stalagmite compared with the amount of precipitation. So we can consider how millimeters of precipitation was changing using these stalagmites in this point. From this study site, we have these 3 stalagmites here, which cover basically the 2,000 years, has almost annual, has 1 point by year. And we see here, this record is basically flat. We don't have strong features during medieval climate anomaly or Little Ice Age or the current warm period. Now in the point 5, we also have a monitoring. This monitoring now has around 5 years, but he just shows some results for the first 3 years. And we also have the collected delta TNU of this the rainfall in this point. When you have more rainfall, you have more negative values of delta TNU, more positive values happening when you have more dry conditions. So also we have a amount effect going on in this region. For this point 5, we have also these 2 stalagmites. These stalagmites show basically what was expected considering the previous reviews when we have dry conditions during the current warm period, wet conditions during Little Ice Age period, but the medieval climate anomaly in this point was not expected because these stalagmites show wet conditions. From the other site, the point 4, we don't have a monitoring, but I have a GNIP station near to our study site. And this is a correlation map between the delta TNU of this GNIP station with the amount of precipitation in South America. Basically, we have a negative correlation between delta TNU and the pluviosity over the South American monsoon domain, which are in blue there in the picture. So basically, the 3 study sites I show you here is a good study sites to understand the amount effect, to talk about the variability of rainfall of the past using delta TNU. Here's the 2 stalagmites of this study site. These stalagmites show what stalagmites has annual lamination, so because that we have a strong geochronological control. And these stalagmites show what was expected during medieval climate anomaly and Little Ice Age period. For example, Little Ice Age was wet and medieval climate was drier. But looking, the anomalies during these events was not so strong. We have actually the values around the average of the record. And the most important features in this record is the seasonal variability. You can see these peaks going up and down. If you measure the distance of these peaks, you see it's happening in a Centennial time scale. When we do spectral analysis in this record, we find these periodicities there in the right, when you have 200 years, 83 years, and 11 years. Basically, all these periodicities is related to solar cycles. And when we perform this wavelength analysis, we see the most predominant periods is this 280 years. Basically, is this, you can see these peaks in the figure at the top. It's very visual, these periods there. When we filter this record in Centennial time scale, we compare with the records of solar irradiance, we see when we have higher solar irradiance, we have a stronger monsoon. Lower irradiance, we have a lower monsoon. This is interesting because this broken the relationship which is South America monsoon have with North Hemisphere. Because when we have higher solar irradiance, we expect the North Hemisphere becomes with higher temperature than South Hemisphere. Because that, it is supposed to go to north. But here show the opposite. When you have higher radiance, we have stronger monsoon. So basically, this time scale, in Centennial time scale, is disconnected with North Hemisphere temperature. The variability in South American monsoon. And now here, I'm putting all this record in that square together. And we see here, when we compare, the records actually very different between them. We don't have a common condition in South American monsoon system. This is very evident during the Little Ice Age period. If you look at the point 1 in northeast of Brazil, we see very dry conditions. If we go a bit more to south and west, we have moderate dry conditions. And going more to the middle of the square in the point 3, we have neutral conditions, but it basically not show any features in the Little Ice Age there. Going more to west, the signal is opposite. The delta T is more negative, you have more wet conditions at that point. You're going more to west, more to south, we have very wet conditions. So basically we have a transition, the moisture is going between point 1 to point 5. We have a dipole between southwest of this square with northeast. You have all the transitions there. So basically, ITCZ, what's considered the main main force in front of South American monsoon, can explain this diversity inside of this middle of South American monsoon domain. Other interesting feature in this comparison, the abrupt anomaly climatic events periods like Little Ice Age, Middle climate anomaly, is more evidence during the borders of monsoon. In the point 1 or in the point 5, opposite phases. But in the middle of the monsoon, the points 3 and 4, we don't see so strong anomalies during the delta O during the medieval climate anomaly Little Ice period. But in these records in the middle, we see more strong centennial and multi-decadal variability, which is in the middle of that square. Just to quantify the anomalies during the Little Ice Age was going on in these records, here's the delta anomaly of each record. You see the point 1, we have a very positive anomaly. In the point 5, you have a very negative anomaly. Between the records in the middle, we have all the transitions of the moisture going to point 1 to point 5. And since ITCZ not be considering an explanation to explain what's going on inside of South American monsoon domain, we need to try other alternatives to explain. One possible alternative could be ENSO. Today, when you have an El Niño event, we have dry conditions in northeast Brazil and wet conditions in southeast Brazil. This fits well with what we are seeing during Little Ice Age period. But when we compare the records in this belt, the point 7, 8, and 6, and 5, they show basically similar conditions, which was we saw in the previous review. And with exceptions in the medieval climate anomaly in point 5. If this happens, if El Niño condition was predominant over Little Ice Age, this is not possible because the region of the Andes has a different signal respond different ways of El Nino than southeast of Brazil. So also Enzo can explain this relationship. Probably what's going on here is the shift of the South Atlantic convergence zone, which are exactly in the middle of the monsoon. But what drives the South America convergence zone is still a question. We can try to work with this in the future. So my main conclusion is South American monsoon was not homogeneous of South America during the last 2,000 years, which was which we see in the previous papers. We put more data together, we see there's a lot of difference. This is more evident during Little Ice Age period, which we have a transition of the moisture in between these regions, but also in other periods, and also in multi-decadal time scale, we have some periods of phase and antiphase. The ATZ position not could explain what's going on in South America, maybe could explain just the amount of moisture going inside of South America monsoon, but not explain the distribution of this moisture inside of the South American monsoon domain. Regions in the border of South American monsoon show more stronger anomalies during global climate events like Little Ice Age period, current warm period, but the Centennial multi-decadal variability more highlighted in this record in the middle of Brazil. Thank you.
So I'm going to be talking about a new stalagmite record that we've produced from northwestern Madagascar and how that relates to the Madagascar monsoon. I work at the University of Massachusetts Amherst and at MIT with Steve Burns, David McGee, and Ben Hart. We also work with Laurie Godfrey. She's a primate anthropologist at UMass, and so there's a really interesting megafaunal extinction story that goes alongside this, if anyone is interested later. And then we also work with Luva and Peterson at the University of Antananarivo, without whom this wouldn't be possible. So our kind of traditional view of tropical rainfall is influenced by this idea of an equatorial dipole. The classic long-term speleothem records correspond to precessional variability, typically local summer insolation, and this has set up a north-south antiphase relationship in the strength of the monsoons, whereby you get more intense monsoons at periods of higher insolation. When we look at shorter timescales, such as the last 2,000 years, this relationship kind of starts to break down. One of the leading theories at the moment is that tropical rainfall is related to the interhemispheric temperature gradient, which is shown in the black lines on the left plot. And this fits fairly well with rainfall from the Sahel over the last 100 years, with the Cariaco Basin after the last 1,000, and with monsoonal records over the Holocene. But all of the records shown in this plot are from the northern hemisphere. And so when we go and look at southern hemisphere records, we get kind of a different picture. Valdir has explained how the ITTZ movement doesn't really explain the South American records. We get a similar picture in the Indo-Pacific warm pool, whereby we find that our northern hemisphere records are behaving as expected. It's getting drier in the subtropics and it's getting wetter on the equator. Whereas when we go and look at records from the southern hemisphere, we're finding a similar pattern, that we've got wet conditions at the equator and dry conditions at the subtropics. And this doesn't fit with our dipole view of tropical rainfall, and instead it's more of a tripole, whereby we've got expansion and contraction of the tropical rain belt. Alternatively, these expansion and contractions also look like zonal variability from Walker circulation. And the idea of expansion and contraction has a relatively simple mechanism. During times of low precession, the solar variability is dominated by the variability in insolation is dominated by solar and volcanics, and this ends up being symmetrical about the equator. And while we might expect that asymmetrical climate forcing would produce an asymmetrical response to the ITCZ, it appears that the local effects of sensible heating on the landmass are able to create this expansion and contraction. So if we've got strange things going on in the Indo-Pacific warm pool, we've got this kind of strange things going on in South America, so we decided to turn to Africa instead. Oh, sorry. This idea of tripole versus dipole is probably best typified by these two papers by Ron Denniston and Deniz Aroglu. These two papers were published 3 days apart, covering the exact same time period and using stalagmites from the exact same caves. And they showed the completely opposite results. One had the tripole and one had the dipole. So we're looking at Madagascar. It's on the southern periphery of the annual ITCZ movement. Madagascar is a very rural population that is very vulnerable to hydrological changes. They've recently been going through a 2-year extreme drought, and then just a couple of months ago, they were hit by a very large cyclone. So understanding past rainfall variability is very important for the lives of millions of people in a kind of a very poor country. The rainfall on Madagascar is controlled. It comes from two main sources. During the austral winter, there is the trade winds, which bring moisture from the east. Central highlands of Madagascar run down the spine, and this creates a rain shadow effect, and so there's a very strong east to west rainfall gradient. In contrast, during the austral summer, the ITCZ moves south over the island and bringing rainfall, and this creates a strong north to south rainfall gradient. Our cave site is located in northwestern Madagascar, and this means we're isolated from the winter winds, and so we should just be a record of monsoonal variability. Our cave site is the yellow square, and so most of our moisture is coming from the western tropical Indian Ocean, and very little is kind of making its way over the mountains. And so this creates this very strong annual cycle, and the annual cycle is dominated by highly convective thunderstorms. And this means that it's highly likely that the delta 80 of the rainfall is related to the amount of rainfall that's falling. So we used stalagmite AB2. It was first published a couple of years ago in Bern et al. 2016. We came back to this stalagmite. We resampled it at higher resolution, so we're almost annual. We added some new dates, and we're focusing on the oxygen isotope record, whereas the initial paper focused on the carbon. The main result is that most of the variability in our record is at the decadal scale, about 3.4 per mil. And this is quite a large variability at the decadal scale compared to a lot of stalagmites. It doesn't correlate with any regional climate indices or index, such as the Indian Ocean dipole, ENSO, solar variability, local sea surface temperatures. The instrumental record in Madagascar is pretty poor, so we're not able to refine the chronology over the historical period. And there's also no significant cyclicity in this record. And this is not unexpected. It fits with this idea that there's no real stationary teleconnection or relationship between the regional drivers, regional climate drivers, and SSTs and rainfall in the modern climate. And it's a good example that sometimes your climate record doesn't have to match everybody else's climate record. So instead, we're going to look at the lower frequency variability. And we're going to make comparisons, firstly with Oman, which is our northern hemisphere counterpart, with East Africa, which is our equatorial counterpart, and with Flores, which will reveal cross-basin relationships. First, we filtered the record to between 50 and 300 years. This removes the decadal variability and the long-term trends, but it's a wide enough filter so that we're not prescribing the result. And what we see is a in-phase relationship with Oman rainfall over the last 800 years. There's a sequence of about 10 peaks and troughs, which match, for the most part, very nicely. So when it's wetter in Madagascar, it's wetter in Oman. The keen-eyed amongst you will notice that there is one peak which is out of phase in the middle of the 17th century. And this is during one of the largest forcing periods of the Little Ice Age. And so that this suggests that during the relatively modest forcing of the last 2,000 years, we have this in-phase relationship which fits with the idea of expansion and contraction of the tropical rain belt. But during periods of larger climate forcing, then we revert back to the more meridional, traditional north-south translation. We also ran a Bayesian changepoint analysis to look at the Centennial scale variability. This analysis looks for changes in the mean delta 18O. It introduces overly abrupt transitions and flat mean states, and these shouldn't be taken literally. But it's still a useful statistical tool with which to at least look at the broad Centennial scale. And what we find is we have 3 dry periods before 500, between 1000 and 1500, and after 1900 AD, and then 2 wetter periods in our record. And so we also ran the changepoint analysis on the regional records, and we find that there's a regional coherency to this pattern. We have wet periods. The later wet period is also found in Oman, it's found in Lake Chala and in Lake Naivasha lake level records. The earlier wet period is found in the bit index from Lake Chala. And so there's a regional coherency to these records. We are anti-phase with Lake Edward. This is to be expected because the Lake Edward record responds to Atlantic moisture. So the regional coherency of the rainfall doesn't fit either with the idea of north-south translation or with the idea of expansion and contraction of the tropical rain belt, and instead implies that we might have a zonal relationship going on, controlling rainfall over the entire Western Indian Ocean region. The fact that all of these sites have rainfall seasons that cover the entire year, plus our orographic isolation from atmospheric zonal precipitation in Madagascar, rules out low-frequency atmospheric IOD variability as the primary driver. So instead, the most likely cause, we believe, is some kind of low-frequency sea surface temperature mode, as all of these records have the same source moisture area in the tropical Western Indian Ocean. So if we have a regional coherency, and we believe this might be best explained by a zonal mode, the question is what happens in the cross-basin relationships. Do we have dipole behavior akin to kind of a low-frequency IOD? Do we have whole ocean behavior where the east is the same as the west? That might be controlled by the Indonesian through-flow, for example. Or do we have regional behavior where the east and the west Indian Oceans are largely acting independently? And so to test these hypotheses, we look at records from the Indo-Pacific warm pool, and we find that the Flores record, again, fits very well with our wet, dry, wet pattern, while the Indo-Pacific warm pool SSTs show the opposite relationship. I think we have to be careful with this, as both of these records are highly likely to be influenced by Pacific climate variability. And therefore, at the moment, I'd say that there isn't a decent record with which we can test this hypothesis that we're coming up with. So to summarize, the in-phase relationship between Madagascan rainfall and Omani rainfall at the multi-decadal scale over the last 800 years does not exist when meridional forcing is strong, but when you've got relatively modest forcing, there seems to be this nice in-phase relationship. Meanwhile, at the Centennial scale, we have a regional coherency of precipitation, which is explained by neither translation of the ITCZ north or south, nor contraction and expansion of the tropical rain belt. The disparate wet seasons suggest this is not an atmospheric climate phenomenon, but rather probably a low-frequency zonal SST mode. But this is kind of quite difficult to test at the moment. Thank you.
Thanks, Nick. That was really interesting. I was just wondering what the comparison looks like if you use ball gown cave those Kimberley speleothem records for looking at the eastern Indian Ocean?
There appears to be no relationship, neither in phase nor anti-phase. Those records don't show that much centennial scale variability, I think. I think they're much more at the decadal scale as well.
Hi, it's my pleasure today to present our research progress. And I actually represent our research team based in Academia Sinica in Taipei, Taiwan. We start, oops. Sorry, okay. So we started this REACHES project in 2015. The purpose of this project is quite straightforward because we aim to build a high-resolution temporal spatial historical climate database for East Asia. And we also aim to reconstruct a very high-resolution climate patterns to enhance understanding of climate dynamisms and the variability across time and space in past 2K, and to explore the relationships between climate change and human society. So since we are mainly dealing with the historical records, which means that we need to be a very highly interdisciplinary collaboration among different disciplines. So now we have research staff from meteorology, geography, history, historical linguistics, who can help us to make sure that we did correctly interpret the historical words, and that might be very different from the current interpretation we have right now. So we take over different researchers take over different parts of the research works, and then we collaborate and have very intense communication with each other to come out this project. So here is the outline of my talk today. So I have done the first part, and then I'm going to discuss more about the inter-contradictory of the historical records to introduce you the strengths of this by using these records, its limitations, and the possible methodological improvements for the analysis. And then I'm going to introduce you our current data statistics and our climate reconstruction in the 17th and 18th century. And then I'm going to introduce you the sensitivity test of our database and some reflections for conducting this research. So, as being said, we are dealing with the historical records. These archives might include the official weather documents, diaries, or church journals. That being said, all these written subjects, all these written records are subject to written histories. Those records must be written, and it's also subject to writers' subjectivity as for how they will interpret these meteorological events. So let's use this diagram for example. The red curve shows the dust fall in the past 1,000 years. So as you can find that very briefly, a growing dust trend after the 16th century. So is that really a growing dust, or you can see the lower frequency of the dust? Does that mean less dust or just less records? So I think as a researcher that's conducting this kind of research work, you need very careful about what does your data telling you. So that being said, actually we are facing some challenges from reconstructing climate from these historical records. So let's face it, that's the limitations. And so what we propose now is to build a more reflexive approaches to test those historical data. So what we are proposing to do is to set up a big data set. In this data set, you probably can have a large volume of records. And by using this volume of records, you can do normalization or even standardization to understand your data, and then you can do some sensitivity test than just to conduct your data analysis in a more robust way. So what does this mean? I will introduce you more in the following slides. So this is our primary data source. It is a Chinese compendium of meteorological records of the past 3,000 years. This compendium is edited by Zhang, Professor Zhang. Some of you might already know about this compendium. Very briefly, it has 4 volumes, and total pages cover over 3,600 pages. Time coverage over 3,000 years, and the spatial unit is quite infinite. It's like a city, county to province level, and this is compendium, of course. So as Professor Zhang said, his colleagues spent over 20 years to review over 8,000 local chronicles and to compile all these records together in this huge book. So we are starting from constructing the data from volume 3, which is the Qing dynasty from mid-1700, that is from the modern minima era. And so only within this volume 3, only within this volume 3, we have collected over 49,000 records in our data set. So that is very briefly, this is the information structure of the records. You have the imperial year that can be transformed into Gregorian year, and you have your province, and then the city, county in that province, and the following meteorological events. So, for example, that can be a Changping County in Beijing, and here is an event describing a very windy haze in spring and in March. So all this information of the records include event, time, duration, and location information that allows us to build a very high resolution climate reconstruction. So this is a framework of our project. With every records are started with pre-processed and digitizing. And then according to its contents, every record's content and our meteorological ontology system, we can decompose the records and give it the corresponding coding codes that can be put digitized in the data set. And temporalization and locating is automatically undertook by the computer programming system. So this is like a relational database management system in our whole process. And after every record have been processed, it can come into the data management system, and then we can retrieve data from the analysis. So this is one of the examples that is in Hebei province in 17th century. So in Jize County, it describes continuous rain in spring, great harvest of wheat. Only this event, we can decompose it into time, event, and location categories, and the texts are coded into the numbers, and so that we can put it in all the records in a CSV file for extraction, retrieving data. So that is a brief snapshot of our ontological structure of the meteorological events. We have 3 main categories comprising meteorology, hazard, and other phenomena. Under every category, we have subcategories. For example, you have precipitation, temperature, obscuring, wind, and cloud under meteorology. And I noticed that many of people, they are interested on flood, drought, or even social phenomena or solar phenomena. So everything in this compendium are coded in our database system. So only, as I mentioned before, only the volume 3, we have a huge number of records in the database system. So we are very careful about the digitizing and data building processes. So we have undertook at least 2 rounds of checks for every record, so the accuracy rate approaches 88%. When I say that is accurate, it means there's consistent interpretation of different researchers to interpret that records, and there's no coding error for those records. Okay, so here is the data distribution in the space. So on the colored dots shows that the places that we have records. So as you can see, they're mainly focusing on the east part of China, and it can be divided into several different geographical regions to allow us to do regional variability comparison. And the red one is B, green one C, and the yellow part, the southern part of China, is D. Okay, this is the qualitative statistics for on the records. As you can see, most of the records fall into the categories of precipitation, flood, drought, and agricultural. And this shows the total number of events every year, and you can see the time evolution of these events. And D has less data compared with B and C. So that is the data profiles. And since we have done this, so we have much confidence to say that the following analysis could support a more robust and positivist climate reconstruction, and to allow us to do normalization and standardization. I will talk about more later. For the data analysis, we did frequency counts, and that is not only the frequency counts, because we put a denominator to understand what is the weight and what is the significance of the events in that certain year. So we use the indexes of precipitation, flood, drought, agriculture, and you can see the time series of these different indexes. And you can see that temperature is lower in the 17th century, but precipitation seems to be a little bit more in the very beginning. And you can see the patterns of flood, drought, and different indexes. And we can also do Pearson linear correlation to understand their relationships. And here we did also grading to understand the seasonality, because as you all know that area belongs to monsoon region, so there is probably some obvious seasonalities in this whole eastern part. So the blue curve shows the north B, and the red shows C, the green one shows D, and you can see the summertime in the left and wintertime in the right. And they actually are kind of consistent with each other. Of course, you can find that sometimes the southeast disagree with the pattern in the north or center, but it shows probably the changing region of monsoon, even within same periods, they probably can have some spatial variabilities. So we also compare our reconstruction with LME data, and the black one shows the LME results, and as you can see that they accept some time periods that are a little bit inconsistent. Actually, our reconstruction and LME present quite a consistency throughout the whole period. And for the temperature anomaly, you can find that it's very interesting, because you can find the LME model data sometimes can represent the southern temperature behavior more than the northern or central China. So, I mean, there are absolutely large regional variabilities, that LME did not catch up for this example. So, except general reconstruction, we also extract some extreme events to do spatial temporal analysis. For example, this is a map that shows the summer snowfall in China. And as you can see, that we are surprisingly found that most of the summer snowfall events occurred in in mid-latitude rather than in high latitude. And we are quite confident about this finding because we found that the data density in the northern part of China is actually more intense than the this central China. So it means that summer snowfall is more easier to happen in the mid-latitudes. That is especially along the Yangtze River plain. So except this, you can also find the time reconstruction of the summer snowfall phenomena. And as you can see, you have more frequent summer snowfall corresponding to mountain minima. And we are very surprisingly to find that the occurrence of summer snowfall in the 18th century actually have very good correspondence with the solar cycles. There actually are only two cycles we did not find the corresponding record, but we found that is lucky eruption, and another one is another VEI5 volcano eruption. So we are not very sure about the mechanisms of the the role that volcanic eruption played in this summer snowfall event. And this is also the spatial temporal analysis for locusts, which you find the locusts can distribute to the very west in the mountain minima. So we also did some experiment to test our data sensitivity. As you can see, that is, we did standardized anomaly to compare annual and seasonality record, and they are sometimes quite different. And we also compare that if we retrieve different data, considering annual data or considering seasonal data, you can find the result can be very different. So retrieving data is a very important issue in this time reconstruction from our perspective. So here's the concluding remarks that we found that historical records can enhance our reconstruction, but we need to understand more the validation and verification methods. And this high data density can help us to understand more about the spatial and temporal variability, and especially we can screen low and high frequency signals. And multi-index can allow us to build up a multi-dimensional climate reconstruction and to discover more to reconstruct the whole atmospheric conditions in relation to the general circulation. So we are now preparing some manuscripts for submitting to journals, and we are planning to release all these compendium volume 3 data later in this year or early in next year. Thank you.
So an amazing data set. I just have one question. In your matrix of different parameters, there was this category called odd rainfall. Do you have any idea what black rain is, or blood rain, or some of those other categories?
Well, we found that odd rainfall can be related to, how to say that, tornadoes. Yeah. Actually, we also found some similar records in Australia diaries, so yeah.
Thank you for this fascinating presentation. Just 2 small questions. I was wondering, your methodology, the precipitation indices, do they connect to what has been done in Europe by Christian Pfister and others? So this kind of putting climate historical data into indexes. And second question is, your database, are you in contact with the Tambora database in Freiburg, Germany, which has a comparable approach, but of course limited on Europe more or less?
Just like I say, we started this project in 2015, so we are now just setting up our data set, but we are actually very much looking forward to have more collaborations with researchers in this area across the globe, especially the European researchers. Yes, thank you.
I think it's a continuous effort to expand the data set, and I was wondering what's your next step, going backward or forward, continuing to the 20th century, early 20th century, or going backward to the 16th or 15th century? We start
building up our data in 1644 is because that is the very beginning of Qing dynasty, and obviously we can find that there are more data in Qing dynasty than the previous dynasties. That is why we choose to start from here, but now we are tracking back into the histories to build a longer-term climate reconstruction. Yes.